Hey everybody, this is Donnie, and I am really happy today to be talking about one of my favorite things, programmatic recursion. So without further ado, let's get into it. Recursion, by definition, is actually very simple. It's just a method that invokes itself. So I have three sub-bullet points here just to kind of qualify that a little bit. There's a thing called the stack overflow, which you've probably heard of before, and you have to follow a certain set of rules if you want to avoid stack overflows. So the first two bullet points are you want to make sure that you invoke the method itself with altered parameter values, and you want to include logic for a base case. So that probably means nothing to you right now, but that's what we're first going to be exploring before we get into some of the more gory details. So recursion is a method that invokes itself. Here are two examples of methods that invoke themselves but will result in a stack overflow. So, the words that programmers usually use for nameless functions are foo and bar. I don't know why, but I did that. So the first function, foo, will call foo, and then when that calls itself, again, it will just continually call another method within the method over and over and over again forever until the machine runs out of resources. So that's actually what a stack overflow is. It's when you keep calling a method from a method from a method from a method forever without having any logic in there to stop it, and you eventually just run out of resources. The second method, I have made it better, but unfortunately it still results in a stack overflow. So even if I say, well, I'm going to put a parameter I in here, and let's say I call bar 0. So the recursive call is going to actually be bar 1. And then the next call inside of that next method will be bar 2. But unfortunately, that will also keep going forever. Right? It will just keep incrementing the parameter value that we invoke the function with, and it will, again, result in a stack overflow. So usually the first thought that goes into people's minds when they're thinking about this is, well, how many times can you call a method inside of a method? How big can the stack get? So that's the note at the bottom. There is no exact number for maximum stack size. I've actually done some research on this, and it's very hard to calculate exactly what it is dependent on your hardware and software. So it's based on a variety of hardware and software factors. In general, you can expect the potential for a stack overflow if you are recursing several thousand times. So you don't really have to worry about it if you're writing an algorithm that's going to be recursing, several hundred times or even maybe 1,000 times to accomplish a task or to solve a problem. Recursion is a valid and powerful tool to solve many algorithms. You really don't have to worry about stack overflows unless you make one of these basically two mistakes that I have shown here. So how do you not get a stack overflow? So this is simple recursion. The most simple example of recursion that I could think of, and I wrote this in Java obviously, was to basically write a method that says, hey, print this text I times. So you can see in the main method I'm saying print this multiple times, and I say I want you to print hello world 5 times. So I could have wrote a for loop here, which any sane person would have done to print out hello world 5 times. However, I wanted to show the simplest example of recursion that I possibly could think of, so I used recursion here. So notice there's 3 comments in the code. Right here, if you can see my mouse, right here I have base case, right here I have implementation, and down here I have recursion. So let's talk about what these three things do. In the previous examples where I said, hey, this would be a stack overflow, we would just be focusing on this one call here. This is the recursive call. The recursive call, again, to reiterate and to be clear, is the call where the method calls itself. So notice up here, I'm saying print this multiple times. This is the number of times I wanted to print. And I am changing the parameter value, like I said at the beginning. You want to alter the parameter value at each recursive call, because if you never change the parameter value, then the call will never be any different, and it will never know when to stop. So that's the first step, is making sure that the recursive call contains a modified parameter value. So up here when I'm saying print this multiple times 5, the first time I call it, it will say, oh, I'm going to call print this multiple times 4. And then the next time I call the method, it'll say, oh, I want to change the 4 to a 3. So it'll print. It's going to call this method with a value for I being 543210. this part is easy, the implementation. That's just what you want the method to do, if anything. It could just be a recursive call, or it could do something and then make a recursive call, which is more likely the case. And this is the important part. This is the difference between this slide and the previous slide, the base case. This is the most important thing to do to avoid a stack overflow. If you do not have a base case, you will get a stack overflow. So the stack overflow examines the altered parameter value to check to see if you're done. In this case, it's very simple. So I'm counting down from 5 to 0. So in this case, I say I've called the method for the 5th time, and I'm saying, wait, I is 0. That must mean I don't want to recurse. I don't want to call the method this time. So this will kick out and basically unravel all of the previous method invocations. So, obviously when you make a recursive call, it will push another invocation of print this multiple times onto the stack, and it will keep building up until it hits the base case when it doesn't actually call the recursive call, and then it will unravel the stack. So I have that showcased here, the stack and the base case. So what I've done here is I've put a breakpoint on the return statement in the base case. So at this point in time here, where I've frozen and taken a screenshot, I have it. I have a breakpoint set, and I have it paused where it has finally hit the base case. And as you can see over here in the stack on the debug window, looking at the stack, it started on the main program. It called print this multiple times, 1, 2, 3, 4, 5 times, which is what we wanted. And then once it tries to call it a 6th time, which is what we're seeing here, it says, no, I'm not going to hit the recursive call. I'm going to kick out of this method, and I'm never going to get to line 12, which is the recursive call. And by the way, see that little icon there on line 12? That's IntelliJ being smart enough to tell you, hey, be careful, this is a recursive call. So that's the gist of it. It's simple, but you need to make sure that you think about what your parameter value is, how it's changing each time, and you got to have a base case, or else it'll never stop and it'll stack overflow. So that's the definition of recursion. That doesn't really tell you what it's useful for yet, but that's the definition. So the first step is understanding what programmatic recursion is, and it's this, I guess at this point it looks like a more complicated way of doing a for loop, but the funny thing about recursion is it's simultaneously simple and extremely complicated. So it's simple in the fact that it's just a function that calls itself, but it's complicated in the fact that once you have recursive calls in there, it's kind of hard to keep track in your mind of the stack, and maybe not in this case, but as we get into more complicated algorithms. So usually the first example of recursion as a problem solver in algorithms deals with the Fibonacci sequence. It's a really great introduction to solving a problem with recursion. The Fibonacci sequence is a famous sequence of numbers in mathematics where the number is always the sum of the previous two numbers. So 5 is 2 plus 3, 8 is 3 plus 5, 13 is 5 plus 8, 21 is 8 plus 13, and it just keeps going on like that forever. So that might seem like simple and random and maybe useless, but if you kind of bear with me, you'll see that that's not really the case. So for now, just understand the Fibonacci sequence is always a series of numbers where the number is the sum of the previous two numbers. So that's what that is. And if you graph out the Fibonacci sequence as a two-dimensional pattern, it starts to get more interesting, and it kind of leads you in this general direction to where it's going to start making sense as to why it's maybe not so unimportant after all. So you can see, we still have the same situation where 5 is 3 plus 2, 8 is 3 plus 5, 13 is 5 plus 8, 21 is 13 plus 18. It's the same sequence of numbers that we saw before. The only difference here is that we're representing it as an area. So we've shown these basically as squares of the base number. So this box is 13 by 13. So it's interesting because if you take it a step further and kind of transpose an arc onto the graph that touches all of the edges of the insides of the boxes, you get a shape that looks like this. So this is starting to get more interesting because that looks somewhat like some things that we might see in real life. So maybe it's not just an unuseful series of numbers after all. Maybe the Fibonacci sequence is not that inapplicable to real things. And in fact, let's take it a step further. And so this kind of gets rid of the backdrop of the grid and the swirly line, and it just shows you pretty much exactly what the area of a shape in 2 dimensions starts to look like when it follows the pattern, or should I say the behavior of Fibonacci growth. So that's like the key word. Like as Fibonacci growth continues, every incremental step of the way, for example, something might get twice as big every time, like in an exponential growth. So, every year something gets twice as big as it was before. This is a different form of that, where everything gets larger as a sum of the previous 2 increments. So it's a very interesting exponential growth. It's not pure squared. It's, the only way to express it is saying it's Fibonacci growth. So, and the really cool thing about this, I think, is that it manifests itself in nature in ways that most people aren't aware of. So many multicellular organisms like people, plants, basically, things that grow. Atmospheric dynamics, so you can see at the bottom middle, there's like the pattern of the storm growing, the wind swirling. And on the bottom right corner, you can see, even in the universe, like cosmological expansion, there's, definite signs of the universe expanding in a way that is aligned with the exact mathematical growth of the Fibonacci sequence. So, all of these examples, whether it be organisms, meteorology, or the cosmos as it expands, these things show clear signs, very precise, clear signs, undeniable signs, to be honest, of following that pattern of growth. So that's kind of philosophically what the Fibonacci sequence is. So this is just kind of to show you that not only is it a great first introductory implementation of recursion, but it's also a very meaningful series of numbers and an explanation of exponential growth in a lot of real world scenarios. So it has scientific relevance. So, I don't want you to think that the Fibonacci sequence is useless, and just an example of recursion. So if you watched, which hopefully you did, my video on analyzing, interpreting, and implementing algorithms in general, you know that you want to start with some single cases and then eventually generate a base or a general case. We already kind of know the general case. I already said it's the number itself is the sum of the previous 2 numbers. However, just in case it wasn't that obvious to us and somebody just showed us these numbers, we could draw out the single cases. We say f of 3 is 3, f of 4 is 5, f of 5 is 8, f of 6 is 13. Right? These are all the single cases. And as we keep going down the tree, we can do these single cases forever. Luckily for us, like I said, we know the general case already, but one could just look at this without knowing the general case and observe the pattern that each particular value is the sum of the previous 2 values, if pattern recognition is a skill that you happen to possess. So there's the general case. The general case is f of I minus 1 plus f of I minus 2, which is just the fancy mathematical way of saying add the previous 2 numbers and you'll get the correct value. Keep a mental note of the mathematical notation of the sequence because we're going to need to recognize that and use that when we implement it. So fib of I equals fib of I minus 1 plus fib of I minus 2. That's the general case. Simple as that. What are the base cases? Well, as we can see at the bottom here, we can't take this number, this 2, and add the previous 2 numbers because there aren't 2 previous numbers. And we can't add the previous two numbers to the 1 because there aren't two previous numbers. So even though we can use the general case on every other number in the sequence, we can't use the general case on the 2 or the 1. So for those, we really need to just call those base cases. So if somebody asks for f of 1, we're not going to say, well, let's figure out f of 1 minus 1 and add f of 1 minus 2. It just makes more sense to say, oh, we recognize this is a base case, the answer is 1. Same thing for f of 2. We recognize this is a base case, the answer is 2. So once again, in order to implement the Fibonacci sequence, we really just have to understand the general case is fib of I equals fib of I minus 1 plus fib of I minus 2, and that the two base cases are if the value they're asking for is 1 or 2, we already know the answer. It's 1 or 2. So it should be no surprise to look and see that the code is extremely simple. So we, in the main program, I'm just printing out fib of 5. And the implementation of the fib function is exactly what you would expect from a recursive algorithm, as I've shown in multiple previous cases, where you need a base case and you need a recursive case, or the general case. And like I just explained in the last few slides, this code reads exactly like what I just said. It's really easy to read. So the two base cases are just either somebody's asking for 2 or somebody's asking for 1. Hopefully nobody's asking for anything less than 1, but just in case they did, I said return 1. And in all other cases, you simply recurse and say fib of I minus 1 plus fib of I minus 2. So this is not just a recursive call, this is a double recursive call. So there's two recursive calls inside of the definition of fib. And you'll notice that I printed out fib of 5, and the value was 8, which is correct. So that's how you implement the Fibonacci algorithm. It's as simple as writing the base cases and then calling the recursive call. So finally, I just want to say that I'm trying to work you guys slowly to the point where you can look at a very complicated algorithm and be able to implement it from conception to analysis to specific cases to general case to implementation to testing. In my last video, we did that with a linked list, which was not a recursive algorithm. Now we're doing it with including recursion. And armed with these tools, at this point, we should be able to work our way towards more complicated algorithms, which we'll be working with in the second half of the semester. So the two skills combined, the ability to analyze an algorithm and move it through the different stages of implementation that we covered in the last video, and understanding some algorithms that may be recursive by looking at the presentation that I've given today. Hopefully with those two skills combined, we could move on to more complicated algorithms. Just to give you an example, not to scare you or anything, although this probably will scare you, this is something that I like to practice a lot, is coding more complicated sorting algorithms. This is from Wikipedia, the pseudocode for a merge sort, which is a very fast order n log n general case sorting algorithm. And basically, I don't expect you to look at this and understand it right now, but I just want to show you what a more complex algorithm might look like in pseudocode. Right away, without even reading the details of this, I can see up here, it's called merge sort, and I can see down here, it says merge sort, and it says recursively sort both sublists. And then I can see down here, there's a function called merge, which is obviously a subroutine because there's no other function on the screen here. And if we proceed down Wikipedia a little bit, it then defines what the merge subroutine looks like. So this is not as simple as the Fibonacci sequence. This is a complicated recursive algorithm that is somewhat challenging to implement, at least more challenging than the Fibonacci sequence. So that's what I'm trying to say, is the goal is to be able to move you towards looking at algorithms that are this big. I probably wouldn't ask you to do something too horrible, but to be able to look at complicated algorithms like a merge sort or a quick sort or something like that, and be able to analyze them and be able to implement them. So I just want you to understand what my ultimate goal is on this kind of little journey that I'm taking you on step by step. So that's kind of it. Hopefully this video was helpful to you. And with that, I will see you later. Bye bye.